In this section of the course, we want to look at how batteries work because all of the circuits we've looked at to this point have been battery powered. Battery powered devices are also called DC devices for direct current. Batteries were first introduced in early 1800s, and the first electrical circuits were all DC powered. So that includes the devices like the telegraph and the telephone. They're all battery powered devices. In fact, if you have a landline in your home today, if you had a power outage, you would notice that your telephone would still work. That's because the DC power that powers your telephone is actually coming from the central office. It's two of the four wires in your modular phone jack are actually carrying power to your telephone device, so it works off the DC power provided by the central office and the phone company. In fact, understanding the role of batteries is important. Alexander Graham Bell had to use batteries in order to power his first telephone devices, and when Bell spilled sulfuric acid on himself, leading to his famous first words over the phone were, "Watson, come quickly, I need you," he was calling for help because of the accident he had with the sulfuric acid. We'll see the role that sulfuric acid plays in a battery a few slides later. Also, analog phone lines to this day are still DC-powered phone lines, and the analog signals that we've looked at previously work well with the analog type of devices that DC-powered devices can govern. The other type of power we looked at was alternating current or AC power, and that didn't appear until much later in the 19th century. Around 1870 or so, generators were becoming commonplace and alternating current was being used then. But in order to understand how batteries work, we first have to look at the molecular properties of water. We'll take a look first at wet cell batteries, and in a single molecule of water we have two hydrogen atoms and one oxygen atom, H2O. Now, hydrogen is the most reactive element and the most abundant element in the universe, and hydrogen simply has one valence electron in its outer shell. Oxygen has 6 valence electrons in its outer shell, and it would readily accept 2 more electrons, one from each hydrogen atom, to bond to it to form water. And so H2O, the water molecule, is very stable. Now, with a wet cell battery, we have both a negative and a positive pole. Those are electrodes. We're going to be connecting our devices we wish to power. The wires will be connected at the positive and negative ends of the battery. And the battery here is a wet cell with an electrolyte type substance that creates a chemical reaction on the poles of the battery. The basic idea is we wish to remove electrons which are negatively charged from the positive electrode. By removing electrons, it makes the material slightly more positively charged. If you remember our atomic diagram of the copper atom, copper has 29 electrons and also 29 protons in the nucleus. So there's a balance, and all the elements have that property. The atomic number of the molecule, for instance, with oxygen, it's atomic number 8. It has 8 electrons and 8 protons in its nucleus. So the act of taking electrons off of an atom, such as lead, which will be used in this case, will make that material slightly more positively charged. Now, if we can remove the electrons from this pole over here, if we could deposit them on the other pole, we can make that pole more negatively charged. And by doing this, an electrolyte facilitates this chemical reaction by stripping electrons off the positive pole and depositing them on the negative pole. Will create a potential difference between the two poles and be able to connect a wire up to either pole and have an electrical current through that wire. This is the basis for DC power, or direct current power. So the idea is to find an electrolyte and two poles made of material that will react in this way. So here we have a wet cell battery. This is a lead acid wet cell battery, and the electrolyte is sulfuric acid, H2SO4. And the two poles are made of lead and lead peroxide. Lead is chemical symbol Pb, and PbO2 is the lead peroxide. These materials react in this way. The sulfuric acid is the electrolyte that will strip off electrons from the lead peroxide, making this pole more positive, and lead will accept those electrons, making that pole more negative. And so the rate of the chemical reaction determines the degree of potential difference or voltage difference between the positive and the negative terminals. The positive terminal on this end is sometimes also called the anode, and the negative terminal is also sometimes called the cathode. So two other terms meaning essentially the same, anode or positive terminal and cathode or negative terminal in this battery. If we look at a dry cell battery, this is a typical cutaway section of a flashlight battery. And here we have the carbon rod in the middle, and the top would be the plus terminal, the positive terminal, and the bottom would be the negative terminal. Now there's an insulator that separates these two materials. The positive terminal is a carbon rod, and along the outside we have aluminum, chromium, and zinc chloride. Aluminum and zinc chloride will be the source of the electrons, the negatively charged particles, when we complete a circuit. Now, while the battery sits on the shelf in this state, no energy is discharged. But once we connect a wire between the positive and negative terminals, then the flow of electrons from the negative end will be directed towards the positive end, and the battery will start to discharge. We can do the same thing with wet cell batteries. Here we have a 6-cell car battery that has a total of 12 volts. The 6 cells each have one lead and one lead peroxide plate in it in a bath of sulfuric acid and as an electrolyte. And the cells are connected in series. By connecting them in this way in series, it has an additive effect on the total voltage difference from the negative terminal on this end of the battery over to this side, to the plus terminal on the right side of the battery. Now, each one of these cells is roughly 2 volts, and so 6 cells at 2 volts each adds up to a total of 12 volts, and this would be a typical 12-volt car battery. Here we have a flashlight, and the similar additive effect can be seen here. We have 3 C or D cell batteries in the handle of a flashlight, and when the switch is closed, we close a circuit that goes clockwise through this metal connecting rod, through the bulb, which is a load or resistance, and through each of these batteries, back out the spring coil at the bottom, connecting to this switch and circulating once again. So this clockwise rotation of the electrons is going to be the flow of the DC current that powers a flashlight battery. Each one of these cells is a 1.5 volts, and 3 in series like this will add up to a total of 4.5 volts that'll power the light bulb. The flashlight bulb here on this end, on the right end, will serve as the resistor, and the resistance is what makes the filament glow and cast light. The flow is in the clockwise direction because the negative electrons come off of this end and complete the circuit here, being attracted to the positive end of the top battery, and these negative electrons flow to the positive end of this middle battery, and these electrons flow again to the positive end of the last battery, adding for up to a total voltage difference of 4.5 volts. Here we see the equivalent circuit for that flashlight from the previous slide. Closing the switch completes the circuit such that the electrons flow through the light bulb, glowing the filament, and being attracted to the positive end on this battery, jumping that gap, and being increased as they come around and complete the complete rotation. Now, if we look at the wet cell battery, we have a similar thing going on when that energy is being discharged. The negative electrons from the lead end on the cathode, the negative terminal, flow through the wire, through a lamp and filament, making it glow, and come and deposit themselves on the positive terminal end. Now, as this reaction goes on, as more electrons travel that path, the positive end becomes less and less so positive, and the negative end is becoming less and less so negative. They're becoming more neutral, or back in balance. And when we've completely discharged that energy, the battery will no longer conduct electricity in this way. Also, during this process, the lead peroxide PbO2 is being converted to PbSO4, or lead sulfate. And the same kind of reaction is happening over here on the lead end as well. So lead sulfate is this white crystally powder, corrosive type of material we sometimes see on batteries. It's often seen on the plates or electrodes of car batteries, and it's formed when the battery is being discharged. When the battery is being recharged, the lead sulfate is being transformed back into lead, and the sulfuric and sulfuric acid separately on the negative terminal, and this chemical reaction can be seen here. Now, this is the recharge cycle of the battery, and so we place a positive end here as though we were jumping this battery with another energy source, and it reverses the reaction. The water in the electrolyte reacts with PbSO4, making it PbO2 again, lead peroxide, and the same thing is happening over here, making the PbSO4 reacting with water, making it lead once again.